with my students, we sort of joke when I give a talk with a black background, I'm doing my thought leader talk. So this is a sort of high level talk about sort of what I think is happening and what are the important trends, and not a detailed technical talk. So when I give those, usually it's a white background because there are lots of plots and things. It makes it easier to make it in a white background. So just give you a sense of what to expect. And I'm thinking about what the future of RF looks like. So we'll go over a few things. All right. So I'll start with a general introduction and maybe a couple funny things about where we are and a little bit about ASU and myself. And then I'll do a overview of what I think are important developing areas. And that'll cover things about some stuff about radar and communications. And then I'll talk some about enabling technologies. And part of that will be some of the processor development that we're working on. Just, you know, ASU is a funny thing. So I think particularly people on back east sort of don't even know that ASU exists. So Arizona State University was established in 1885, which was well before Arizona became a state. It wasn't Arizona State University at that point because there wasn't an Arizona State. But it was a college then. It was established in 1885. But you know, for the first almost decade of its life, it was a relatively large state school, but kind of sleepy. Over the last 20 years, there's been a complete change in the direction of the university, and we went from effectively having no noticeable research to, well, you can see from the chart that we're over $640 million per year in external research, and we have sort of every intention to get past $1 billion in the next few years. So it's a big school, but it's also a big school in terms of the amount of research going on as well. We also have the largest engineering school in the U.S. And electrical engineering, we have about 78 faculty. That's always changing a little bit. So last time I checked, it was 78, and about 36 million external research. There's a little bit of confusion because computer engineering is split between electrical engineering and computer science. It's formally over in computer science, although there are lots of people doing computer engineering and electrical engineering. So if you were to count all those people, we'd be probably well over 100 in terms of faculty. Only because this is mildly amusing. So I started at Arizona State, graduated a long time ago when dinosaurs roamed the earth and all that. While I was there, I worked at Motorola, GEG. I then went to work for General Dynamics, and I started off by doing rocket avionics. So I worked on the upper stage of the Atlas Centaur, which they then started just calling the Atlas. So I worked on the thrust vector control, the electronics for the thrust vector control. Then I worked on magnetic field optimization for superconducting magnets for particle accelerators, which was a lot of fun. Although they killed that program, although some of our work and research ended up going and being used at the particle accelerator at CERN. Then I went back to school, UC San Diego, and got my master's and PhD in physics. And I did, even though I was going to San Diego, bad life decisions, I spent almost all my time at Ithaca, or in Ithaca, doing my research at Cornell University, when I could have been in San Diego. So what can you do? Then I went, and when I was done, I went and worked for Lincoln Laboratory, which is a Department of Defense technology research laboratory that's run by MIT. I was there for 15 years, and then strangely, I came back to Arizona State, which is really, I mean, it may seem not very remarkable to you. To me, it's hilarious, because when I left, I enjoyed ASU, but I had never had any intention of coming back. I didn't have any intention of coming back to Arizona. I had no intention of going back to ASU. And at some point when I was looking, I was thinking about going back to academia. I didn't even have ASU on my list. I had a number of universities sort of on my list I was looking at, and I stumbled across this article about ASU, how it completely changed. And I was like, oh, I guess I have to think about that. And now here I am. All right, anyway, so let's think a little bit about engineering at a very high level. So no one is doing this now, so I apologize. This is a terrible example, but this is the one I have. When we used to fly, sometimes we would rent cars, and when you would turn a rental car, there are basically these big garages in most airports, and those large garages, you know, when you returned it, you would drive up, and there would be like these columns of car, and somebody would sort of guide you to drive up and pull up to the car behind it, and then somebody would walk out with an iPad or some sort of tablet, and they would enter, you know, just a few bits of information, some car ID, whatever the gas gauge is, and probably something about are there any problems with the car. It's basically a few thousand bits of information. I mean, it's a tiny amount, but it is a pretty complicated environment. And so if you look around, what you'll see is, oh, there's a Wi-Fi router sitting there, and you're like, well, that makes sense. You know, everybody uses Wi-Fi for everything, so they're probably just talking to that. And then if you start looking around, and I've done this before, you're like, oh, there's another Wi-Fi router that's not that far away. And then you look around a little bit more, and you go, there are Wi-Fi routers everywhere. And this makes no sense at all, because you know, it's not a lot of data. There's reasonable power. You should be able to send that signal if you had designed the waveform properly, you know, a kilometer. But the problem is we use the waveforms and protocols that we're handed because we're stuck with them. There's some custom system on chip that somebody spent $1 billion on basically establishing, and now that it's really cheap. So we have these super cheap chips that do a small subset of standards, and we use them for everything because we only have a hammer and a screwdriver. So whatever the problem is, we're going to use a hammer and screwdriver. And it turns out there are lots and lots of other problems, and we tend to not think about it because we only use the solutions we have in hand. And I claim that gets us in sort of this rigid trap. That is, we have certain computational capabilities that limits our engineering options and reinforces a certain set of requirements. And we get stuck thinking about problems and using the solutions that we were handed, as opposed to stepping back for a second and saying, well, maybe that's a good solution. Sometimes it is. Or maybe there's a much better solution. So we're thinking about, you know, how to break that stuff. So I'm a director of a center at ASU, Wireless Information Systems and Computational Architectures. And we want to go from sort of new concepts to implementations. I'm a strong believer that you can't just do paper studies, you have to build stuff. Often what you find out is, you know, if you come up with paper studies, that's good work, it's potentially important work, but you know, more often than not, you've missed important portions of the problem until you go build it. Now, the downside is when you go build stuff, it's a horrible pain, because when you make hardware, nothing works. And then you realize that you have to go fix that, and it still doesn't work, and you go fix that, and then it's like it kind of works. But that's life. And so in order to get that sort of real life understanding, you have to go through the pain of actually building stuff. Fortunately, flexible SDRs have become widely available, software-defined radios, and we can do a lot with those. And so that's nice. So it used to be that if you wanted to do something like this, it was an investment of $1 million in your lab and you know, potentially a dozen staff years to get it all working. Now we can do a lot of work much more quickly, and we've taken advantage of that in our center. So we use EDIS radios. We have a couple dozen EDIS radios, for example. We also sometimes build our own custom SDRs for special functions, and we do a lot of experiments. And here you see a photo of my now research scientist. He was a graduate student when he was flying this, flying a DJI S1000 Plus, which is an octocopter, and it actually can carry a fair amount of weight, and we can put SDRs up on that. We play various, do various experiments with those. And then sometimes if you want to do complicated stuff, you got to go worry about the actual implementation. And so I have a big processor development program. I'll tell you about that a little bit later. And we've had lots of funding from lots of different sources, which has been great. So over the last 4 or 5 years now, we've had a lot of funding, more funding from DARPA than anyone else, but certainly Google and Viasat, Google and Airbus have given us a fair amount of funding and lots of other entities as well. So I'm thankful to all them. All right, so important developing areas. So let's think about, you know, what do we need? We're going to have to support a much wider range of user types. You know, for the longest time, you could be human-centric and be just fine, but that's clearly changing. The vast majority of, quote, users are not going to be humans. That's already happening. And we need to increase the node's real-time flexibility. A human will typically have a certain characteristic set of needs, and while we may think of that being very wide, from sort of voice to maybe downloading a video, in the overall scheme of things, that's actually not that wide a range of data rates. We get used to maybe recharging our phone every other day or so, or every day, every other day, which we just get used to doing it. But if you think about it, that's ridiculous. I should be able to go a month without recharging my phone. But so this is where we are, right? So that's all based on sort of human characteristics. And when you start thinking about other kinds of users, maybe they can't charge the phone, maybe they have different sorts of needs. And then maybe really more speculatively, we have a history of being very isolated in our use of spectrum. We assign a certain piece of spectrum to this use and another piece of spectrum to that use. And we're very careful about keeping them far apart and not letting big signals be next to small signals. And it's complicated. And you know, there are huge organizations that dedicate their lives to making sure that people don't step on each other and make it all work. And I appreciate that. But it's also based on certain assumptions about the technologies involved. And we can be much more sophisticated than that. All right, so non-human users. I mean, the non-human users already dominate radio use with the advent of IoT. It's just going to grow at some point. Human users will be some tiny subset of the overall number of users that are of RF. And we're probably not talking about Disney characters. Sadly, we're probably talking about internet toasters. I have no idea why anyone needs an internet toaster. But anyway, so these types of users require, can require a much larger dynamic range of performance. So they might go from a keep alive that's sending a bit per day to trying to dump, multi-dimensional sort of 3D images, video captures for short periods of time and doing all sorts of complicated things. And then going back to sending out a bit a day for a year. And that's the kind of thing that humans just don't do. And then a much wider range of computational range. So you have something where maybe it's measuring a temperature to having to reconstruct from a set of images, the 3D position of everything, right? And so that's a huge dynamic range. And it turns out the processors we have are not very good at high dynamic range processing. That is, they're sort of designed to operate at a particular computational rate and can't move away from that very well. I mean, you could always just sort of stop doing computations, but their power consumption doesn't go down that much, maybe by an order of magnitude, but the computational dynamic range might be moving around by 9 orders of magnitude. So, so we need to think about how that all works. And, if you have, frankly, disposable systems that have, or the DoD likes to use the word attritable, that is, you may not go recover it, then you might need much lower cost and size, weight, and power for these objects. So these are all the things we have to have in the back of our head thinking about this. Another thing which is a real potential, I think, at this point, it's not what people do right now, but it's a real potential, is to use or implement systems that have distributed coherence. And by distributed coherence, I mean actual phase coherence, carrier phase coherence, so that you can use these distributed radios as an antenna array, and multiple users. And as more users show up, you can basically have a bigger array, a bigger antenna array. Okay, I just saw a chat, so I figured I'd see what was going on. So in order to do that, you have to figure out how to get all these nodes to agree on the frequency and the actual phase itself. So I'll tell you some more about this, but we worked on some phase-accurate time transfer techniques. I actually, back when I was at Lincoln, built a system that took a number of distributed radios and cohered them up, and it would actually transmit phase coherent signals to a receive node. It works. I think we were the first people to do that. And now we're extending some of those thoughts. And there are lots of advantages of this. Potentially you can mitigate interference, but the simplest advantage is that if you have n users, each one of these users is putting out some sort of unit power, you phase cohere these up, then the power at the receiver can go up by n squared. So that is potentially a huge effect. All right. So another part, which I've already alluded to in the very start, is the idea of fluid communications. Need to address the needs of non-human users and frankly our needs as well. And you want to be able to match the waveform to the environment, which right now there's some ability to do that. Standards have some ability to be a little bit flexible, but I claim they need to be far, far more flexible. So we want to break from that. So you might have some environmental situation, you might have certain data rate needs, you might have a certain observed delay spread, certain amount of Doppler spread. Maybe there are lots of users, maybe there are a few users. And what you would like to be able to do is just adapt the waveform, adapt the protocol to that particular situation, and quickly have everyone agree on it, and you would get much better performance. All right, so, and I refuse to refer to this as fluid communication standards. Additionally, if you're going to have these sorts of things, you want to have the computations match it. So you could say, oh, I'm going to have this sort of big range of data rates or other sort of computational abilities, but you need to have the energy efficiency sort of stay with that. So that's an important system goal, which is very often ignored. And if you actually try to make a system where it is, the computations are good at high performance scenario, and you get good computational efficiency in terms of power at a low computational scenario, then what you find out is there are other parts of the radio which then dominate the power consumption. The bane of my existence is frequency synthesizers. So I've had more systems give me grief because of bad synthesizers than any other problem in my life, and they're really devious problems. They hide from you and then pop up when you're not looking and cause things to break. Anyway, they also have a problem that if you try to, say, reduce their performance and by sort of try to turn down the power, there isn't a good way to sort of say, oh, I'm willing to put up more with more phase noise and maybe lower accuracy, but do that at lower power. There's no scaling. There's no good way to actually make these things happen. So you have to really think about the entire system and the power consumption of all the components of the system to try to make one of these scalable systems, and it's hard. All right, so another technology which I think is coming and it's starting to happen is what I call personal radars. Now, of course, the first sort of wave of personal radars you may already have, and that is probably every new car in a few years by law probably will be required to have a radar on the front of it to make sure that it doesn't get in an accident, which will be nice because it'll probably save lots of lives. But I'm even talking about smaller radars. So you can imagine radars that are tiny and they can measure things only a few meters away. There's lots of information that can be gained. And the nice thing about this, as opposed to a camera system, is you can do this without being quite so invasive. So people either should be, or people are, or they definitely should be sort of concerned about privacy issues with having cameras trained on them all the time. But you can imagine having a radar system which is not as invasive. One example of a radar was developed by Google, the so-called Google Solely radar, which was designed to do gesture categorization for hand motions and estimation. So the idea is that you could take your hand and move it a little bit, and we're very good at certain types of motions, not the motion of moving your finger across a screen, but things where you rubbing your thumb and your index finger, right? We're very good at precise movements with these motions. You can imagine using those motions to control things for some sort of computer interface to your phone, without actually even having to take your phone out of your pocket, because the signal will go right through your clothes. And so you might be able to control things very precisely and do all sorts of motions and have it controlled that way, which is kind of cool. An area which we've been working on a lot in our lab is actually physiological measurements. So the blue line is actually an extraction from real data, where we were pulling out the individual R to R pulses, signals in a cardiac signal. So that you see each one of those pulses. It turns out you can use the R to R interval. It is potentially an indicator of future cardiac distress. And so we're studying this. It's a difficult signal to actually deal with, because it's, or to estimate, because your breathing is close enough in frequency that it causes artifacts. So we've gotten fairly good at disentangling the breathing and the heart rate, and we can measure the heart rate at lower SNR scenarios and the individual R to R intervals for high SNR scenarios. And I think there are lots of health benefits of this, elder care benefits of this, and lots of other sort of personal situational awareness potential applications as well. All right. And then RF convergence, in some sense, this is the most general form of fluid standards. Let's stop trying to separate different RF functions. So we can reuse RF signals and receivers for multiple functions simultaneously. So a simple example is you have desire to know about what's going on in the cars around you, and we already have radars. There is actually already a standard for vehicles to communicate with each other, although as far as I know, it's almost no system uses it. And it's interesting. So our first instinct, of course, is to build a radar system, and then to build a separate communication system. So I have 2 full RF chains. I have 2, everything, it's all separated. And I'm still trying to talk to the vehicle in front of me. And it turns out the communication link between the vehicles is actually not very good at the one that's established in the standard. Whereas you could have, if you use the RF energy from the signal going out in front of you, you could potentially have a very high data rate signal that's low latency, and you already have something pointed at the vehicle you care about. So it's high signal to noise ratio too, and of course we ignore that and we go, oh, comms has to be in a different spectrum, but we could reuse the same energy and do multiple things simultaneously. Everybody is talking about using millimeter waves for 5G. People are building phones with millimeter wave front ends. I don't know if that's going to be a win in the end, but you could certainly imagine that you can reuse that same RF front end, so it can do gesture control and it could do millimeter wave communications. So why not, right? I have the capability. We should pursue that potentially. And then of course there are plenty of DoD applications for these sorts of capabilities as well. I'd like to be able to do all my communications radar and whatever else I want to do with the RF energy at the same time and the same frequency. And then I think the basic idea is we need to stop thinking about segregated RF systems and rather think about, I have RF nodes. It's a heterogeneous set of RF nodes. Some are high power, some are low power, some have advantage positions, some don't. But how do I build a joint system that gets data wherever I need it to go and jointly estimates wherever I'd like to estimate all at once? So that's basically the idea of these RF convergence. People also use spectrum sharing, although I think spectrum sharing also sort of includes just dealing with other users in the spectrum. I'm really interested in spectrum co-design. I think that's the future. There are lots of different sort of ways or different kinds of topologies that you can imagine. I think you can see my mouse. So you can imagine a scenario where there's a single user that is trying to do communications, reuse that same communication signal to do to basically bounce off some sort of target, some scatterer, and he goes to receiver. And this is sometimes referred to as passive radar. Maybe you have a TV broadcast, and I'm just using reusing that TV broadcast to do something passively. But maybe I'm actually designing this waveform so it's a good radar waveform at the same time as being a communications waveform. So that's more like this one where I'm trying to actually communicate, and not only am I trying to use my waveform to do target estimation, target detection to target estimation, but I'm actually reusing that waveform to actually talk to the receiver. So this receiver is jointly doing radar functionality as a bistatic radar and communication functionality. Same receiver, same time, same waveform. You can also imagine I have multiple users doing this as well. You can imagine I have a radar, quote radar, that is I have some RF node, which is acting as a monostatic radar and at the same time doing a comms receiver. Because often radars are in advantage situations, or ground radars anyway. And so why not use that as a communications receiver simultaneously at the same frequency at the same time? So that's an interesting set of problems. And here's an example of a radar as a relay. So it's doing, it's receiving a signal, and when it goes off and does a monostatic radar operation, transmitting off to some target so I can figure out where it is, at the same time, it uses the same waveform to actually do communications as well. So this radar is jointly estimating what's going on in the environment and working as a base station, if you like. One of the reasons to just sort of like to throw up a bunch of different example topologies is that sometimes when people talk about RF convergence or spectrum sharing, they're talking about the waveform design, and that's not that's a valid area to be investigating. And sometimes when people are talking about it, they're talking about the receiver design, and sometimes they're talking about the whole system design. So when you go look at some sort of RF or spectrum sharing paper, your first job is to figure out which kind of topology they're actually talking about, because usually when people write papers, and I've probably been guilty of this myself, you just assume that the only kind of problem that you're going to work on is the kind of problem that you're working on, and you ignore all the other sorts of topologies, and then the reader starts off thinking that you're going to work on something else, and this is probably a standard problem across all of academic papers, is we all work on what we work on. Anyway, all right, so we have gone through and thought about this a bunch, and so here's one example where we're talking about this multi-access receiver. So let's go through sort of a system block diagram. So the radar is acting like a monostatic radar. What it transmits in this case, what is basically a standard radar waveform, potentially the standard chirp. Now, it'd be more interesting if we actually sent out a communications waveform, but here we're going to start with just a simple example. It goes to the radar channel, it comes back, and at the receiver, it's summed with a communication signal, which goes to the comms channel. And what we can do is we can remove the predicted return from the radar, because what you're going to see is that you've been tracking maybe this target, so you kind of have some expected signal returns. So you can remove what you can predict. You can't remove everything, but you can remove the portion you predict. You can decode the comms. You can remove the comm signal from that, because you can project onto a basis which is orthogonal to the re-encoded signal that you decoded. First thing I do is decode it, and then you can remove that part of the signal, and you can do radio processing on the residual, which combines the residual from this and the predicted portion of it, and you can get the radar information. So it sounds a little bit complicated when you sort of walk through the steps, but actually computationally everything you do here is not so far from the kind of things you would have done anyway. So we've done this in the lab. I told you we have tons of EDIS radios, and here's an example where we did some of this work. So this is an example, a simple example where we had a communication signal which is sitting on top of a chirp. So you can see the right up chirp here, and what we're receiving, and this is real data, over the air data. So what you're receiving is the comm signal looks like it's sort of interfering with the radar signal, and the radar signal looks like it's interfering with the comm signal. So you can go through that block diagram that we discussed before, and this is the same data on the right. And what we've done is we've decoded and remodulated and projected onto an orthogonal temporal basis and remove the communication signal, and we're left with what is almost a perfect representation of the data as if the comm signal wasn't there. So you can do more sophisticated versions of this, but this is a nice example of, it's not a joke. You can actually do this stuff over the air, and the hardware doesn't stop you from doing it. this is a simulated example. We have a fairly sophisticated simulation that does multiple communications signals, wideband communication signals going over the air. And we build a synthetic aperture image, and it's actually a multiple aspect one because we use those comm signals going over the air to first decode it. So you have to go through and figure out how to do the successive interference cancellation to get the multiple signals out. And then we use those as references, and we can build multiple synthetic aperture radar images from those comm signals. So this is like a different topology where I'm reusing the same signal to jointly do communications and as a radar illumination waveform. And did everything I need to actually build synthetic aperture radar images from those communication signals, which is kind of fun. All right. We can go through and do this a lot, you know, but all the examples that I sort of talked about so far have been fairly simple ones. You know, one of the things you have to worry about is I have something which I call the estimation rate, which is sort of how much information I'm learning about the target. Of course, there's a comms rate, and maybe there's a relay comms rate. You can imagine you can come up with all these metrics, and pretty quickly you can run into a situation where you have far more dimensions than I can plot. Because real life tends to be more complicated than the simple topology that you see here. But even in this scenario, or well, rather, in this scenario, I can actually write down some sort of optimized set of parameters for all the characteristics of the system. And depending on what I want in terms of how important is the relay, how important is the radar, I can come up with some optimal set of parameters that will perform the best as I move my needs along the surface, right? So I can do that. The next set of problems is that when I have lots of nodes, they may have stale information. Figuring out how to optimize that huge space of parameters with a huge number of users and multiple goals simultaneously, that's a complicated problem. I certainly don't know what the answer is, but there's plenty of work to be done there. All right, so enabling tech. I think we all owe analog devices because when the 9361 came out, they put what used to be some complicated flaky board onto a chip. And life got a lot better because now all of a sudden everybody was embedding 9361s into other devices, ADAS radios. And of course now there's a whole family of these sort of RF front-end chips. And now what would have been an expensive design, custom design, is now having these flexible RF front ends, throw it in a box, you can play with these guys, and it really helps all of us who are doing you know, experimental radio systems or even radar systems. And the next part is sort of the advances of FPGA. So the Zinc processor is a really useful chip. We've used it a lot, and the RF-SOC actually it's basically a Zinc with some A to Ds and D to As built into it as well. These end up being great tools for more sophisticated software-defined radio systems. You're trying to be a little more sophisticated. Unfortunately, the programming FPGA fabric is still pretty hard, and probably always will be. They keep on trying to do high-level language converters for this, but the truth is that's just hard. Maybe someday. But you know, with some work, you can actually do real implementations on these things, and then you can go change them when you need to. So these sorts of technologies really have changed the ability of people like us, academics, to do real over-the-air experiments. And I should also say, you know, the 5G technology is really bringing sort of this grab bag of things, whatever 5G is. All I know is our next phones will say 5G. I don't know what technology they'll have in them. But, you know, the important stuff, carrier aggregation and millimeter wave and sort of the massive MIMO or MIMO, lots of small cell stuff. There's lots of commercial tech which we can go grab and then, exploit for our research purposes. And I think there's going to be a lot of fun stuff with millimeter wave antenna arrays that we're going to be able to use for doing new kinds of experiments. So it's kind of an exciting time to actually be trying to do communications or RF convergence sorts of experiments. Yeah. So another thing which I think is probably interesting as well. So let's just talk about the flying car problem for a second. There are lots of people that are interested in urban air mobility, and it turns out in order to legally fly automated systems, you need to be able to position them to within 10 centimeters. So you can potentially do this with really good Kalman class filters and GPS. The downside is anybody who wants to can go spoof GPS. So it's embarrassingly easy. So that's kind of dangerous. And not only that, even when GPS is working properly, it still can be easily misled by its own problems. So for driving around in your car, it's not a big deal, because if the GPS tells you that you're off in a lake, you'll go, I'm not in a lake, I'm just going to drive where I need to drive, and you'll override it. But for autonomous flight, this can be a particular issue. So companies like Airbus, I did some work for Airbus, they're interested in supplemental technologies, and one of the things we worked on is joint communications and positioning. So you can use timing exchange techniques, and if you do it right, you can use timing exchange techniques where you can get really good performance. And now this is a different kind of RF convergence problem. So this is joint PNT and communications. Potentially you could use joint PNT communications and radar for that example. I'll tell you what, I'll leave that for later. I already mentioned the distributed beamforming before. If I can actually get knowledge of where every phase center is for some set of nodes, then I can cohere them up and transmit. But that means I need to know their position to within a small fraction of wavelength, potentially with some ambiguities. But we'll ignore that for the moment. And then we can do all sorts of fun stuff and beamform these distributed set of nodes. So one thing we need to worry about is actually figuring out where they are. So we did some work where we, around a gigahertz, a little less than a gigahertz carrier frequency, 10 megahertz of bandwidth, we were able to get to the point where we had a order centimeter ranging accuracy. So if you think about it, 10 megahertz of bandwidth, the sort of intrinsic resolution you get from that is about 30 meters. And we were to split that all the way down to basically order 10 millimeters, a little less. So here's an example where we wrapped our system with a Kalman filter around it. So we were operating around an order centimeter, and the Kalman filter cleaned it up a little bit more and got down to the 3 millimeters. So intrinsic resolution of about 30 meters, and we're getting it down to about 3 millimeters. So we're splitting that resolution cell by a factor of 1,000 in this. And it works. So we actually built a system that works in real time. It actually can converge to within a couple centimeters in 100 milliseconds, and dynamically track the positions as somebody flies around. So this is actually a DJI S1000 Plus. That's our system hanging down below it. This is the ground version. And we can actually track the range, and we actually have multiple antennas on this. So this is really a MIMO system. So we have 16 different links that we're tracking all simultaneously. And so we go from by doing this, we supplement GPS, and we go from a system where it's easily spoofed to one that's essentially immune to it, because you have a communications link, and you could potentially encrypt that. And additionally, the ranging error in this case goes from order of meters, millimeters, to something which is on the order of a handful of millimeters. So this is fun. I think this is all sorts of things we can do with that. So I think another important component of this is that historically, there was a good reason to basically use the technologies that were available, right? There's a good reason to use Wi-Fi chips because they're cheap, it's embedded in everything. Bluetooth is cheap, it's embedded in everything. And even if it's not a very good standard for your particular problem, it's there. And who can fight with that? And one of the reasons why is that the computational efficiency is extremely high. So even though the communications performance might be suboptimal significantly for the environment you're in, or your particular needs. You're still like, well, the computational advantages are so high, I'll put up with it. But what if we could be more flexible in our computations? So what we would like is to develop a system where it has the computational efficiency in terms of operations per watt, and we'd like that to be really high, something on the order of more than teraop per watt. But we like the effort of implementation to go from a new chip design, which would be optimistically only 100 staff years, probably a lot more, to basically something where it's not much harder to program than the scalar processor like the one in your laptop. And certainly we'd like it to be easier than programming FPGAs. So in my lab, we do a fair amount of this, and every time we regret it, but that's the solution we have right now for lots of problems, so we're stuck with it. So we'd like to get to this point where it's really efficient and also easy to use, relatively easy to use. Of course, it's easy to want things. But we think we can actually make progress on that. We're building a heterogeneous SoC, the whole development framework. We're assuring that the non-experts can program this. And we think by doing this, we can actually enable the next generation of RF. So we're trying to open that door. And where's my flying car? All right, so let's do a little bit deeper dive on computations. So you have node technology along the horizontal axis, and you have basically power along the vertical axis, or operations per watt rather, and so the inverse of power. If you take a look at scalar processors, of course they become much better as the node feature size has gone down. Those of you who follow this carefully will know that it's not getting better as quickly as it was before. In fact, we may even getting to the point where going to smaller feature size is no longer a benefit in terms of operation per watt, because the features are just so small that they're actually becoming less efficient. In any case, there's still a sort of 2 to 3 orders of magnitude improvement going from the scalar processor to a full custom ASIC. All right, well, if you take a look at a particular class of operations, so like RF operations, they have a set of tasks typically, which are the expensive set of tasks. Most of the computations are taken up with a small subset of tasks. So an example is a multiple antenna receiver communication system where I'm trying to do some nulling maybe. And so if you take a look at where the computations live, where all the expense is, so matrix multiplies into being really expensive, FFTs potentially are expensive, matrix inversion, which we implement using QR back substitution, and then error correction. These are all fairly expensive tasks. Then there are a gazillion of higher layer tasks, which in fact are relatively cheap. So if we can identify those tasks which are expensive and figure out how to actually get them all to work and build accelerators for those, then all of a sudden we can potentially make a chip which is almost as efficient as a full custom chip and yet can do lots of different tasks. All right, and so this is actually a sort of a very coarse scale view of the processor that we're developing. There's a very high performance network on chip, although it's flexible, so we can reduce power consumption. There are multiple ARM processors on it. We have FFT, fur filter accelerators. We have something called DAP, which I'll explain in a second. There's an intelligent scheduler, which is really key to making this all work. I'll talk about this more. We have error correcting accelerator, and we're debating what other accelerators actually put on the chip. All right, so here's the problem. So we're not the first people to recognize that these sort of coarse scale heterogeneous processors are a good choice for doing many of the problems that we all are interested in. But how do you get something where maybe somebody hands you some C code to something which is implemented on the chip? The problem is that people have done this before, and I've actually worked with chips that other people have built where they're a coarse scale heterogeneous processor, and they had successfully implemented one serious application. One. They built this flexible processor, and the people who made it had only successfully implemented one application on it. And I actually saw the exact same thing happen more than once. And the reason why is the threading of your tasks through that complicated processor is super hard. And in one case, there was the guy who knew how to do it. There was like one person on the planet who was good at this. And if you wanted help, you had to go talk to that person to make it work, right? This is clearly not scalable. So you need to figure out how to solve these kind of problems. So you need to make the sort of threading those applications, moving data around, doing the scheduling, all the resource management. You got to make that a lot easier. And you need to reduce the reliance upon sort of expert development. Furthermore, another problem you have with these sorts of systems, if you send some data into an accelerator, and garbage comes out the other side, you may not know why, right? And if you have 3 different people build 3 different accelerators, the kind of information they provide and the debugging can all be completely different. And it's a nightmare to try to debug. So you got to figure out how to simplify the compiling and the debugging and the scheduling. All right. So this is one of the things this is what we're trying to do. So we start off with a large repository of example applications. These are the things we think are important. We grab some of the stuff from the wild, and we actually have written lots of our own as well to make sure we have the applications that we care about. We do ontological analysis on that. We determine the computational relationships of all of these sorts of things. We then use that information to help us understand what we need for the network, the on-chip network, and for the hardware design that includes the accelerators, and actually even the layout of the chip. Although, unsurprisingly, probably could sort of guess what the right answer is, but it's nice to actually have the software tell you what's important. And then we use that same bit of information, because we know the computational relationships between different kernels, computational kernels in the tasks, to then go and build typically called fat binaries. We've been joking we were going to try to get people to change to call them chimeric binaries, because being someone who's a little overweight myself, I'd prefer not to call them fat binaries. But anyways, that's life. And also, so these chimeric binaries, if you like, you can imagine that, let's say I'm trying to do an FFT. I can do the FFT in an ARM processor. I can do the FFT in the accelerator. I can do the FFT in one of the DAP processors. I could do it in a different variant of one of the DAP processors. So we have multiple ways of executing that task. And so what we do is we carry them all around, and then the scheduler in real time determines how it should actually execute that task. Now we have all this data. We actually go take this data, and we train an intelligent scheduler. And what I mean by that is we have offline oracles that we built. So you can imagine if I have a whole bunch of tasks, what I can do is just produce a sort of traveling salesman problem and try all possible scenarios about how to thread everything through our system. And then there's some good set of solutions. There's even a best set of solutions potentially, a best solution potentially. And we can then take those solutions. And the problem with that is that that's insanely expensive to actually go calculate. I had a student doing it on some of the stuff, and it was taking a day to go find an optimal solution for a particular scenario. Since we need to make decisions on the order of 5 nanoseconds, a day is not going to work. So we have multiple techniques for these oracles, by the way, because the oracle, that kind of oracle is still too slow to be useful, even as an offline system. In any case, what we then do is we use imitation learning, and we build a net that does imitation learning that quickly tries to mimic what we are doing based on the oracle, and it's actually working really well. I'm really happy with how this is working. I mean, to be clear, this is a large team. I'm not personally doing this, but we use that intelligent scheduler goes on the chip, and in the end, we're going to have a real-time implementation. Cross my fingers, real soon now. All right, so We also have some supplements to traditional processors. So we have something called the domain adaptive processor. The domain adaptive processor basically is a very sophisticated systolic array processor. And it allows us to do lots of good linear algebra kinds of applications. And we can instantly change what the DAP processor is. So the nice thing about the DAP processor is that it's an accelerator. It's not quite as efficient as a full custom accelerator, but it's pretty good. It's like a factor of 2, maybe a factor of 3 off of it. And but it is very good. And then instantly we can switch to do other linear algebra sorts of operations really well. All right. And then we also have a unified error correction accelerator as well. It uses some similar techniques as the DAP processor, but it allows us to do a wide range of decoding, which is, if you do these things, you know, it's often one of the expensive parts of this. All right, so I mean, we basically, our ontological analysis, we're actually much better now than 90% accurate. There's this sort of, you know, this is more on the computer science side. There is this sort of trade between trying to do static analysis of code and dynamic. We have this view that dynamic is far more important because static analysis, you can often get off in the weeds and worry about parts of the code that in fact aren't that important. The problem with dynamic analysis is that it's super expensive. And so we've gotten much better actually by doing source compression is actually a big part of our the reason why we're much faster. Software, we basically have now tools that can automatically develop these chimeric binary transformations. We've done FPGA demos of this. We've gone a long ways to standardizing the kernel interface for debugging and things like that. So that's working. Intelligent scheduler, we've made lots of advances in that area. We can get to, at least for certain types of problems, 99% of the Oracle scheduler. And this is fast and computationally not too expensive. The on-chip network we call the DAP, we were able to show and have RTL for something which gets us basically moving data around in 5 nanoseconds. In terms of the hardware, we've developed accelerators for the DAP, the FEC, FFT, FIR. In fact, we're actually sending out the DAP on a test chip real soon. Demonstrations, one of the subs on the team is actually General Dynamics, and they've built preliminary boards. So we're going to take the chip and basically build an SDR out of the chip. They already physically built the first versions of the board, so as soon as the chip's available, they're going to be ready to put it on it. Our schedule for this, you know, we had a kickoff back in 2018, mid 2018. Right now, in a couple months, we're going to send off a test chip to Global Foundries for the DAP. Beginning of the year, we're going to send off the first spin for the processor, and then 2022, the second spin of the processor, which hopefully will really be a viable chip. Not long after that, at least when we get back, General Dynamics will implement a software-defined radio using the chip, and then Collins Aerospace on a sister program will also be doing some other applications. And we're sort of eyeing various possibilities of trying to get the chip up on a small sat to see how it works. I guess on the stat, we call the program Dash. On the chip development program, ASU's a prime, and I'm the PI. We got a big team, of course. This is a big, complicated thing. So ARM is on the team, Carnegie Mellon, General Dynamics, University of Arizona, University of Michigan, University of Texas Austin, University of Wisconsin. And then we have the sister program with Collins Aerospace. So we're really excited about this. And once again, you know, starting at the beginning of the talk, this is basically enabling many of the things we want to do, which require flexible, sophisticated processing. And things, they are changing. So we all have to, the fun part is we like this, right? The downside is don't sleep because everything's gonna go pass you by. So I gave you introductions to sort of ASU and WISCA and me, and we talked about the fun things that are happening in these areas. And key technology that's being developed that's going to enable us to do much more sophisticated things. And that's it.